What's up guys, it's Simon Fiaz and today's video is on AQAS level chemistry um, 2021, June 2021 paper 2 walkthrough. Label the x-axis and figure 1. Y-axis, number of molecules. It says ignore particles slash atoms. Yeah, it says here molecular energy is a sample of gas or number of molecules. State where the curve starts at origin, no molecules have zero energy. There are no molecules with zero energy. No molecules with zero energy. No molecules with zero energy. State what X indicates. Most probable. Most probable energy. Half of the gas molecules are removed. The remaining gas molecules are kept at the same temperature due to the new distribution of molecular energies for the remaining gas figure 1. So it's going to have the same peak. Yeah, same energy in line with X. But it's just half of it because half the molecules are removed. I don't think that's half. I think it should be like that then. But you get the point. Half the gas molecules move, so it's going to be half the area. Half the original area. So label the y-axis number of molecules. Say what the curve starts at origin, no molecules, zero energy. Say what x indicates more probable energy, and then this one, applying your knowledge, half the molecules moved, therefore it's going to be half the area of the original area. Question 2. Alkenes react with bromine. Name and outline the mechanism. Electrophilic addition. Electrophilic addition. And what happens is your Br partially positive, your Br partially negative, and then what happens is it goes from the arrow from the double bond to here to the Br, and that breaks. Br bond breaks, and then what happens is now we've got this, and you've got a Br but here, bonded here, and you've got a carbocation here, one for electron, Br minus goes there. And that's it for 5 marks. Electrophilic addition, double bond to the Br, partial positive, Br bond breaks, and then Br with lone pair electron, negative charge, bonds to the carbocation with positive charge. So there's attraction between a carbon-carbon double bond and Br2. First things first, carbon-carbon is an area of high electron density. The Br becomes polarized, partially positive Br is attracted to carbon-carbon double bond. Carbon-carbon double bond, area of high electron density. Br becomes polarized, partially positive Br attracted to carbon-carbon double bond. So the skeletal form of the halogen alkane formed by butyl-1,3-diene reacts with excess of Br2. Now CH2, so I've got 1, 2, 3, 4 carbons, and I can see I've got 1, 2 double bonds, right? Excess of Br2, so I'm going to form 1, 2, 3, 4 Brs under here then. So first things first, butyl, so methane, ethane, propane, ethane, propane. Yeah, methane, ethane, propane, butane. CH2, but instead of that, I'm going to have a Br here. That's what double bond is. Or I can have a Br here. Or I can have a Br here. Or I can have a Br here. Remember, it's an excess of Br, that's why. Question 3.1, the three problems that apparatus set up in figure 2. Identify the problem, describe the issue, cause, suggest how the problem can be solved. Stage 1, anti-bumping granules. No anti-bumping granules. So add anti-bumping granules to prevent large bubbles or to create smaller bubbles. Stage 2, another problem. No thermometer. Is an open system. Open system with no thermometer. System should be closed above the flask to prevent gases. Why should it be closed? To prevent gases escaping. Should be closed with bung plus thermometer needed as well, to allow, to prevent distillation of other components. So to allow the collection of propanone only propanone they're trying to collect, prevent distillation of other components. Stage 3, the water direction in the condenser. And if you look at it, water out should be water out there, water in there. It's the opposite way around. Water flows in wrong direction through condenser. Condenser not cool enough. Product may not condense. Question 3.2. This should complete the experiment with the apparatus set up correctly. Shouldn't react this much of propane 2-ol, X-acidified potassium dichromate 6 solution. Contain this much of propanone. I calculate percentage yield. So first thing I need to do is find out. I'm going to use density as mass over volume. Mass equals density times by volume, which is equal to 0.786 times by 2. Then I can work out the moles of propane 2-ol by using 0.786 times by 2, the mass, over the MR, which it hasn't told me the MR, but it has given me the formula, so that's pretty nice. So therefore I can easily work out the MR. Let's use some periodic table. So 12 plus 3 plus 12 plus 1 plus 16 plus 1 plus 12 plus 3. You get the moles of that. Then you know they've got a 1-to-1 molar ratio. Therefore, you want to find out the theoretical yield of propanone. So the mass, moles is mass of MR, mass is going to be the moles that I've worked out, times by the MR propanone, 12 plus 3 plus 12 plus 16 plus 12 plus 3. And then I'm going to use that, my theoretical yield, so 0.954 divided by my answer, times by 100, 62.8%. but it does say appropriate number of significant figures, so 63%. So find out the mass by using that. Find out the moles, 1-to-1 mole ratio, therefore the mass of propane expected the theoretical yield, times by the MR, and yeah. Molecules of propane-2-O each contain 3 carbon atoms, shape around central carbon atom, and suggest bond angle. Suggest shape and bond angle. Propane-2-O, tetrahedral. Obviously, therefore, the bond angle is going to be 109.5 degrees. And then propanone, trigonal planar. Once you know the shape, obviously you know the bond angle, 120 degrees. Tetrahedral, 109.5 degrees. Trigonal planar, 120 degrees. So you know propanone has a lower boiling point than propan-2-ol. So first thing I would say is that propan-2-ol has stronger intermolecular forces. Propan-2-ol has hydrogen bonds. Hydrogen bonds between molecules. Whereas propanone has dipole forces and van der Waals forces. So propan-2-ol has hydrogen bonds. Has strong intermolecular forces, has hydrogen bonds between molecules, whereas propanone has dipole forces and van der Waals forces. Question 4. Use our UPAT rules. Wait 1 second. Propanone. Sorry. Use our UPAT names to name CFC11 trichlorofluoromethane. Trichlorofluoromethane. Then it says a molecule of CFC11, so CCl3F breaks down to form a chlorine free radical, Cl dot plus CCl2F dot. Trichlorofluoromethane, CCl3F arrow CCl2F dot plus Cl dot. Okay, question 4.2. A typical refrigerator contains this much of CFC11. One molecule can cause the destruction of approximately 100,000 molecules of ozone. Use these data to estimate the number of molecules of ozone that can be destroyed by this much of CFC11. Give your answer in standard form. So, I can find out the moles of CFC11. I'm not fully sure what I'm doing right now, but I know I can find out the moles, and that's definitely going to help me. Over 137.5, which is 3.64 moles. Perfect. And that will probably give me 1 mark, right? Use this data to estimate the number of molecules of ozone can be destroyed by this much. So I've got the moles, and it says 1 molecule causes the destruction of 100,000 molecules of ozone, and I want to estimate the number of molecules of ozone destroyed by this much of CFC11. So I'm going to times by 100,000. I'm also going to times by 6.022 times by 10 to the power 23, because I want to find out the number of molecules that can be destroyed. 3.64 times by Avogadro's constant, 6.022 times by 10 to the power 23 times by 100,000. Once you've done that, get your answers 2.19 times by 10 to the power 29. State the benefit to life of Earth of ozone upambuses absorbs harmful UV radiation. suggests one reason why the use of CFCs was not restricted until several years after Rowland and Molina published their research. Lack of alternatives to chlorofluorocarbons. Lack of alternatives to CFCs. Then explain how CFC 11 is able to contribute to global warming. Well, it absorbs infrared radiation. Infrared radiation. Absorbs infrared radiation. Molecule has polar bonds. Infrared radiation. Molecule has polar bonds. Question 5. 3 key steps to manufacture polypropylene from crude oil are shown. For each step, name the process, state briefly the purpose, process, at least formation of polypropylene. So crude oil to naphtha, well, what's that going to be? Naphtha to propene, well, that's going to be thermal cracking, because I'm forming alkene, and then propene to polypropylene, addition polymerization. For the first one, crude oil to naphtha, it's going to be fractional distillation. Fractional distillation, and separate into mixtures of compounds fractional distillation is separated into mixtures of compounds with similar boiling points. Step 2, name thermal cracking and make an alkene to make alkenes. Perfect. Stage 3, well, you haven't gone through, if AS level paper and you're in year 1, you haven't gone through condensation polymerization, so then you just say addition polymerization, but do go through condensation polymerization in year 2. Molecules for addition polymerization, obviously, therefore molecules join together to produce long chain molecules. So fractional distillation, separating into mixture of compounds with similar boiling points. Thermal cracking to make alkenes. Addition polymerization, molecules join together to produce long chain molecules. Explain why polypropylene is unreactive. No polar bonds. No polar bonds / non-polar. Suggests why it's beneficial for some polymers to be biodegradable to prevent no to prevent buildup of waste in landfill. No polar bonds / non-polar to prevent buildup of waste in landfill. Calculate relative molecular mass of Y. Okay. So I'm going to obviously use PV because I know T. Ideal gas equation, that's probably maybe the hardest step to identify, because in the rest is rearranging the equation, go and find MR, so then N is PV by RT. Then converting the units, you just need to memorize the correct units. 51,000, measure pressures in pascals, volume, meters cubed, so centimeters cubed to meters cubed, and you divide by a million. R 8.31 gives it in the question. Calibrate temperature in Kelvin, it's already in Kelvin. That will give me the number of moles, and I know moles equals mass over mR. I want to find out relative molecular mass, therefore mR equals mass over moles. and I know the mass 717 milligrams. I need to convert to grams, so it's going to be 0.717 grams. 7 grams over the number of moles. So the number of moles will be 51,000 times by 482 times by 10 to the power minus 6 divided by 8.31 times by 297, and then do 0.717 divided by my answer. I get 72. 72.0 as the MR. And you can speed B over RT, use the correct units, then mass is moles of mass of MR and moles mass of the moles. And then yeah, you get 72.0 to 3 significant figures at least. 6.2 in the second experiment, another flask is used for combustion reaction. And this method, remove all the air from the flask. Add this much 0.001 moles of CH18 to flask. Add this much of oxygen, 0.0200. So I know it's a 1 to 12.5 mole ratio. So if I do 0.00100 times by 12.5, I actually get 0.0125. So that tells me, well, I've got this much, right? This is how much I did. So I've got 0.0200 minus 0.0125. I've got 7.5 times by 10 to the power minus 3 moles of oxygen excess. Is an excess. Right, so that's after the reaction in excess. So I've got that. But I've also got 8 CO2 and 9 H2O. I do not care about 9 H2O because it's a liquid. We're trying to find out moles of gas after reaction. So we don't care about that. Carbon dioxide, we just use the 1 to 8 mole ratio. So it's 0.0010 times by 8. It's going to be 8 times by 10 to the power minus 3. And therefore the total amount of moles of gas after reaction, 8 times by 10 to the power minus 3 plus 7.5 times by 10 to the power minus 3. I get 0.0155. 0.0155 moles. Then it says, name the mechanism for reaction. Prop-2-ene10 can be prepared by reacting alkene with dilute aqueous sodium hydroxide. Wait, what? Propane-2-ene10 is made by reacting 3-chloropropene-1 with dilute aqueous sodium hydroxide. So this is what's being made, right, by reacting an alkene with dilute sodium hydroxide. Nucleophilic substitution. Replace the chloro with the OH group. And that was a bit tricky. I was thinking about elimination. Yeah, that's what I was thinking. Obviously, it's not going to be electrophilic addition, so I was thinking about elimination. But yeah, the answer is nucleophilic substitution. Then it says prob-2-1 could also be formed from this in the presence of acid catalyst, name an outline mechanism for reaction. So I'm going from an alcohol to an alkenes. So yeah, it's going to be elimination. It's going to be elimination. Yeah, it's going to be elimination. Now I can see why. So I've got CH2 CH2, CH2, and this is a tricky part. I need to identify, I'm forming a double bond here, therefore with the oxygen with lone pair of electrons and oxygen bonds to the H plus, it's got to be here. So you've got this, and then oxygen with lone pair of electrons bonds to your H plus. Because then what happens is then you've got this. I guess you leave it here, partial positive, CH2, 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 OH, then from here to there, oh no, sorry, can't go like that, here to here, and then what happens is then you've got this, carbon-cation here, and obviously you can't form a double bond here. Because CH2CH, CH2OH, yeah, it doesn't really matter wherever you do it. And then what happens is then you form the CH2 double bond CH. And then you've got your CH here, CH2 here, OH. And look what we have there. That's exactly that. Draw the repeating unit of polyprop-2-ene10. Repeating unit of this. So first thing I need to do is basically put it in this format where you've got something like that. So it's going to be like C1C H H H, and this then it's going to be here CH2OH. Once I've done that, then I just remove the double bond and then that's it. So oh no, I lied. My apologies. Then it's CH2OH. I need to show all the bonds and then show the sticking out like that. So put it in this format and also show each bond. So CH2-OH, remove the double bond, and then yeah, that's what you get. Repeating unit. The isomer figure 3 shows the interreflection of functional group isomer prop-2-ene10. Isomer Rex's cis potassium dichromate from a green solution. And draw the structure of the isomer. Isomer Rex's potassium dichromate to form a green solution. So we've got this, obviously, prop. Well, because it's a functional group isomer, and you can see the carbon of functional group, therefore it's going to be like that. So find the term enthalpy change, heat energy change at constant pressure. Heat energy change at constant pressure. How well can you memorize the definitions? Use the data to calculate value for carbon bond being propane. I'm given delta H minus 2046. Minus 2046 equals energy required to break bonds minus energy released when new bonds are formed. C3H8, ethane, propane, or propene in this case. One, 2, 3, 4, 6. 3, 4, 6, 7, 8. No, sorry, propane, not propene. I'll just say propene. Propane, C3H8, is propene would be C3H6. Anyway, I've got 1, 2, 3, 4, 5, 6, 7, 8 CH bonds. So 8 divided by 4, 1, 2, plus 1, 2 carbon bonds, which I'm trying to find out, plus 2Y, plus 5O2. Well, O2, O double bond O. So 5 of those is going to be 5 times by 496. Minus energy released when new bonds are formed, 3 CO2. Well, then that's going to be 6 because I've got C double bond O, double bond O. So I've got 2 for each one, and I've got 3 of them. 3 times by 2 is 6, times by 743, plus 8 times by 463. And I also know to go from liquid to gaseous is also 41, so plus 8 times by 41. Actually, no, it's not. It's going to be 4. 4 times by 41. Eight times by 412 plus 5 times by 496. 5776 plus 2y. Almost fall. I did fall for it. That's 4H2O. It's not going to be 8 times by this. It's just 4 because I'm going from one molecule H2O to one molecule gaseous, liquid to gaseous. Just 41 times by 4 because I've got 4 moles. And plus 2y minus 6 times by 743 plus 8 times by 463 plus 4 times by 41, 8326. 5776 minus my answer, and then minus 2046 plus my answer divided by 2, 252. Perfect. And then it says explain why the value given for this O double bond O bond enthalpy is not a mean value. O double bond O, no sorry, oxygen is the only substance that has O double bond O bond. Therefore, that's why the value given for the O double bond O bond enthalpy is not a mean value, because oxygen is the only substance that has O double bond O bond.